Hey folks, so let's talk about the cost of JavaScript. Building interactive experiences on the web today usually involves sending an amount of JavaScript down to your users, often too much of it. So today we're going to talk about why JavaScript has got such a high cost and a few things that you can do to work around that and still give your users a really good experience. So as it was mentioned, I lead up a speed team in Chrome. We spend a lot of time talking to developers about web performance and more frequently, things that they can do to improve the size of their JavaScript bundles. Whenever I come to a developer, they'll tell me that they've been trying to work on their JavaScript for 6 months, and cleaning it up 6 months in can sometimes feel like sweeping up water back into the ocean. It's an uphill battle. And so my team's motto is, if JavaScript doesn't bring users joy, thank it and throw it away. I believe that this was in the post-credits scene for the Marie Kondo special. If you take away nothing else from this talk today, there's 2 things that I'd like you to remember. The first is that small JavaScript bundles can improve your download speeds, they can lower memory usage, and they can reduce CPU costs. This is going to be particularly important around mobile. Memory costs come into play when we think about the uncompressed size of scripts. That script still has to be stored in memory. The second thing that I'd like you to remember is that post-download, executing JavaScript is now the most dominant cost, and so it's important to keep that minimal. In the past, if you've read any of the articles I've written about the cost of JavaScript, I've placed a heavy emphasis on things like parsing and compiling code. That phase is now a lot faster in browsers, and so execution time is something that we need to pay attention to. So let's dive into 2 topics, network and compute. Now, network is all about, trying to get bytes over the wire. How do we get our JavaScript down to those devices that users are going to be checking, our experiences out on? And compute is how do we actually process that JavaScript in a really efficient way? So let's start off with network. Now, as we've seen from some of the talks yesterday, a fast connection is not always fast. In fact, I like to use the free Wi-Fi at Starbucks to complain about how slow their free Wi-Fi is. If you've ever been at a coffee shop, you're probably familiar with this phenomenon that, it can feel like we have a fast connection on Wi-Fi or 4G, but we don't always get, the best speeds. In fact, building on top of something Rick Viscomi talked about in terms of the Chrome User Experience Report, here's a breakdown of the effective connection type for a really big global site. This is twitter.com. And as we can see, we've got users predominantly accessing twitter.com over 4G. Not that many people on 3G. It seems like people have got fairly good network connections. We can also take a look at the effective connection breakdowns for a site like Jumia over in Nigeria. Jumia is a really big site over there. Their proliferation for 4G is not quite as strong as for twitter.com and the countries accessing it. It's about 47%. It's about 57%. Now, the reason I was mentioning that a fast connection is not always fast is that although we often hear conversations these days about 4G and even 5G starting to get more traction around the globe, it's very uneven. Here's a chart from OpenSignal that shows how consistently 4G networks are globally available and the average connection speed that users have on those networks. Now, countries that perform better in the metric are shaded darker. What we can see here is that there's still a huge amount of variance in network connectivity speeds. So if we're talking about network transfer, that's still an important thing when we're thinking about the size of our JavaScript bundles. Let's switch things over and talk about CPU. So JavaScript is CPU bound. The biggest bottleneck in modern mobile web performance is CPU. About half of the web is being accessed on devices where we don't always have the strongest CPUs, don't always have the strongest batteries. And so while transmit sizes end up being important for slower networks, JavaScript execution time is something we have to keep in mind for phones and devices with slower CPUs. Now, speaking of phones, let's talk about phones. A lot of us in this room are probably lucky enough to have a high-end device. You probably have a number of people here with iPhones or Pixel phones or something in a similar class. However, mobile is a spectrum, and it's an uneven spectrum at that. There is a huge difference between a low-end phone that costs $30 and something that's closer to $1,000. Differences in thermal throttling, cache sizes, CPU, GPU. The ability for these phones to be able to process JavaScript can vary quite a lot. In fact, let's dig into this data a little bit more. Here's a charting of the highest selling phones globally from last year. What you'll see in here are phones like, the iPhone 8, the iPhone X, but there's also a lot of Android devices in here. There's a lot of devices that are much slower than iPhones. That fourth phone, the Xiaomi Redmi 5A, that was the most popular phone in India last year. Now, let's try to quantify this. The Apple iPhone has got an A11 processor chip in there. Maybe you know that, maybe you don't. It's got 2 high-performance cores, and that allows it to do things like process JavaScript really quickly. Let's take a quick look at the CPU performance of these devices. And for this, we can use a benchmark called Geekbench. So Geekbench is a popular benchmark. It separates single-core and multi-core performance, tries to simulate real-world scenarios. And what we can see is that the CPU performance for something like the iPhone is vastly different to that for the Xiaomi Redmi 5A or any of the Galaxy phones that you or your family may have. We can, sometimes when I talk to people about CPU performance, they'll say, this is more of an emerging markets problem. Everybody here has got a fast device. I don't really need to worry about this. But that's not strictly the case. If we take a look at Best Buy's top-selling phone list, this is from this week, by the way, we see that the 2 devices on this list are the LG Stylo 3 Plus and the Galaxy S10. Now, these phones vary wildly in their price, but if you take a look at the CPU performance, the single-core and multi-core, the LG Stylo, which is under $200, performs so much slower than the Galaxy phone. So what does any of this have to do with JavaScript? Well, to explain that, we have to dive into how browsers work just a little bit. So I work on a web browser called Chrome, and when you're sending files down to the browser, it looks a little bit like this. It gets even worse with HP2 multiplexing. Wow, there's still a lot of script being sent down. Now, I love JavaScript, but my position on it is it's probably the most expensive part of our sites today. Much more expensive than resources like images or fonts. And it's got a very different cost to it. Byte for byte, it's one of the most expensive things you can be sending down. Let's take a look at some more stats. So according to the HP archive, the median web page is shipping down 360 kilobytes of compressed script to users. These sites take about 9 seconds before a user can interact with them. And if we take a look at the uncompressed numbers for this, 360 kilobytes will bloat up to well over a megabyte of compressed script that devices have to process. We can take a look as well at, say, popular sites. So popular sites are reaching this interesting cliff where it seems to be okay shipping down megabytes and megabytes of JavaScript to our users. CNN is shipping down 2.6 megabytes, The Verge 3.8 megabytes. And the real question is, can you afford to send down this much script to your users? When we're trying to add interactivity to our pages today, we're often paying a JavaScript tax. So what is it that we're sending down? We generally have some level of page logic or application logic. We have our UI library, our framework, utilities. You can easily think of things you've built that probably have a router in place. Maybe they're using Moment.js, other utilities. You'll maybe have a UI library, maybe you'll have third parties in place. But all of these things add up in cost. And it's important to think about whether that cost is something that's actually delivering value to your users. Now, what impact does shipping down a lot of JavaScript have on the user experience? Well, some of you might be familiar with Lighthouse. It's our auditing tool baked into the Chrome DEVTOOLS. It's available via the audits panel. Lighthouse has this time strip at the very top that exposes metrics about the user experience. Now, over the last couple of years, we've been evolving our understanding of what it means to load a web page. And we've kind of broken it down into 3 buckets for metrics of, is it happening, is it useful, and is it usable, and is it useful to users? Now, is it happening is that point when, maybe you've painted something on the screen. Is it useful is when you've provided, primary text content, primary image content. And is it usable is that point when the user can actually interact with the experience and have something happen. Now, if the idea of a timed interactive metric is something that still confuses you, here's a visualization of it. Now, for a page to be interactive, it has to be capable of responding very quickly to user input. Whether that user is tapping on a link, tapping on a custom component, if they can't respond to the page quickly, then it's not really interactive. And there's a good chance that they're going to end up leaving your experience. I experience this pretty frequently myself. So timed interactive is a lab metric. For the field, we've also got a complement to timed interactive called first input delay. And my colleague Katie Hempenius tweeted this out the other day. This was an experience she had when she loaded up a flight website, and the first time she tried interacting with some UI, nothing happened. And so these metrics are important for us to keep an eye on because the JavaScript we're sending down can actually impact folks in real meaningful ways. Now you might be wondering, does time to interactive actually matter at scale? And I think that it does. In 2018, Akamai conducted a UX study into the impact of interactivity on rage clicks using their solution Impulse. And they discovered that the majority of rage clicks were from users who expected to be able to interact from a page in 1.3 times the point when the page was visually ready. So 1.3 times the point when I can actually see some UI. If I tap on it and nothing happens, there's a good chance that I'm going to rage click, rage tap, and maybe I'm going to end up leaving that experience. Another place that we commonly see the cost of JavaScript actually impacting things is rehydration. So if you're familiar with client-side rendering or server-side rendering, rehydration is this idea that tries to kind of combine client-side and server-side rendering by doing both of them. So server-side rendered pages often look like they're ready and like you can interact with them, but you can't actually do that until all of the client-side JavaScript is executed, until those event handlers have been attached, and that can sometimes take seconds on mobile. Now, when JavaScript ends up blocking the main thread, almost nothing else can happen on it. This is something that we need to keep in mind as we're building experiences for folks. Now, when the above code is running, it's not just blocking other JavaScript code. It's blocking all of the other tasks on the main thread. And that can include other so-called native things. So if I'm trying to interact with a checkbox, if the main thread is blocked, I may not even be able to do that. You might be wondering, well, how do I work around this problem? And one way to do it, one way to avoid things that can push out your time to interactive, is keeping an eye on long tasks. So long tasks are tasks that end up monopolizing the UI thread. They're things that take over 50 milliseconds to complete, and they can block other critical tasks from being executed, even if your page looks like it's visually ready. So one thing you can do is try to break up some of those longer tasks, split up your code, prioritize the loading of your code a little bit more carefully. And if you can reduce those long tasks, hopefully they'll have less of an impact on input latency. For folks who have got a little bit less experience with the DEVTOOLS performance panel and are not really sure how to identify long tasks, we actually just landed a change in the Chrome DEVTOOLS whereby if you hover over a long bar of work, we'll tell you if it's causing long tasks. You can then expand that work out. You can see what scripts, what functions were necessary, were involved in pushing the work out, and you can start to try optimizing them. In some cases, rather than doing a bunch of work asynchronously in the same task, you can break those up into much smaller things. Now, in terms of how long you should aim for getting interactive in, we say getting interactive in 5 seconds on average mobile hardware, something like a Moto G4 over fast 3G or slow 4Gs are generally a good target. This person isn't actually interacting with the phone. They're going through withdrawal symptoms because there's nothing on the phone at all. So we want to design for resilience. We want to try building experiences where the cost of JavaScript is not really hampering our users, but is actually empowering them to do more. So how can we do that? Now, to get a better understanding of what this means behind the scenes for JavaScript engines, let's talk a little bit more once again about how browsers work. So you type in an address into the URL bar and you hit go. It fires off a request to some server somewhere. You go through your DNS, TLS resolutions and everything, and at some point, maybe you will get some HTML sent back down, it'll parse the HTML, it'll start to send down some resources for the page, then the browser has to process it. It looks pretty much exactly like this. We have to crunch all of your resources so the browser can understand it, and start to actually do something with all of that script that you're sending down. Now, once we've finished processing that script, hopefully you'll get something rendered on the screen if it was script bound. If the main thread's been blocked, maybe you end up interacting with this page and nothing actually ends up happening. So JavaScript can be a real bottleneck, and it's something that we do need to think about as we're building out these modern experiences. Now, if you want to be fast at JavaScript, you need to be fast at 3 things. You need to be fast at downloading that script, parsing and compiling that script, and then executing that script. If you're spending a very long time downloading and executing code, that can heavily delay how soon a user is going to be able to interact with your experience. Let's take a look at a real-world example, something non-controversial like Reddit. So Reddit has got kind of 2 experiences. On desktop, it ships one version of its site, and then on mobile, it ships another version of its site, which has this lovely kind of prompt to install their native app, which we won't talk about. But if we just take a look at kind of where Reddit.com is spending its time in V8, Chrome's JavaScript engine, we can see that it spends up to 30% of its time just processing script. 30%, that's a pretty significant amount, right? Now, I wanted to point your attention to sort of the blue and the yellow areas. Now, the thing that really matters here is the main thread time. How much time on the main thread are they spending? I've also got in yellow this other thing called background thread time. Now, in most of the talks I give about the cost of JavaScript, we don't really talk about background threads or what that even means. So hopefully this is new to you. I'll try to explain it. We're going to get a little bit into the weeds on this one for a hot second. This is going to feel a little bit like your experience, trying to read a manual for putting together an appliance. Whenever I read one of those manuals and it tells me that it's going to be easy, I feel like, it's really lying to me pretty badly. So hopefully that won't be your experience with us. When we talk about background threads, what we're really talking about in Chromium-based browsers is this idea of script streaming. So in much older versions of Chrome, we had this idea where, we'd first of all download a script before beginning to parse and compile it. And unfortunately, that didn't really take full advantage of the CPU. Around Chrome 41, we introduced this idea of script streaming. And the idea there was that we would parse async and defer scripts on a completely separate thread as soon as the download began. Now, the benefits of being able to start moving more of our work to the background have been pretty substantial. We first of all moved more of our parsing into the background, and then we did it for compilation. Now, background compilation gave us the ability to improve main thread time by 2%. Background parsing and other improvements we've been able to make to parsing have improved load time spent in V8 by up to 20%. Now, in more recent versions of Chrome, we've actually continued to evolve this idea of script streaming. In Chrome 71, we moved to a task-based setup where we could actually parse multiple async and deferred scripts at one time. That led to a 3% improvement in time to interactive for a large swath of pages, and it reduced main thread time by up to 40%. We're continuing to kind of build on this idea as much as we can. But that kind of explains where that background thread is. If you ever look inside DEVTOOLS, it's the background thread time that corresponds to script streaming. So let's take a look at some new charts. For Reddit.com, this is where it's spending its time on a MacBook Pro at the very top. It's spending multiple seconds just processing JavaScript on the main thread. This is a huge amount of time compared to what some other sites are doing. It's a lot of time being spent, not spending a lot of time on the background thread. We take a look at their mobile experience, which really, if we're comparing apples to apples, is the last three of these. We see that processing time on a high-end device like a Pixel 3 is relatively quick. Processing time on an average phone like a Moto G4 is like 3 or 4 times as slow. And then it gets even slower if we look at a sub-$100 phone like the Alcatel One X. We can also take a look for fun at Facebook.com. And now we'll notice that this changes up just a little bit. Facebook.com are spending a lot of time, this is again MacBook Pro, for their desktop site, they're spending a lot of time processing JavaScript, but only a small portion of it is spent on the main thread. Quite a lot of it is spent in the background. We see a similar skew between the performance of this site on mobile devices. But let's try to unpack why we're seeing such a big difference between Reddit and Facebook. So one thing Reddit are doing is they're shipping very large JavaScript bundles down to their users. These are multi-100 kilobyte bundles. And those bundles, they're wrapped in outer functions that's causing some lazy compilation on the main thread. They could probably benefit from splitting those bundles up into much smaller bundles, say 50 kilobytes. Now that 50 kilobyte number is actually interesting because when we talk about V8 script streaming, we actually start streaming once we see 30 kilobytes of code. And to maximize parallelization, you actually benefit from splitting things up in a much more granular and much more coarse way. So Reddit have got large bundles. Facebook are spending 70% of their JavaScript processing time in the background thread. Now here's where things get really fun. They're actually shipping 6 megabytes worth of script down across 292 requests. That's a lot of script. But what's happening in Facebook's case is that they've got their scripts so coarse that they're actually able to maximize parallelization, maximize our ability to process and compile everything on those background threads. Now, you're probably not Facebook. You're probably not, something like a Gmail where you're a long-lived app. So maybe don't ship 6 megabytes of JavaScript down across almost 300 requests, but do try to break up your work. So if you're trying to ship experiences efficiently and you want to go on a JavaScript diet, here are 3 things you can do. You can first of all reduce how much JavaScript that you ship. Maybe only load the code that the user needs for the current route or the current view. Avoid those large JavaScript bundles. If your bundle exceeds, say 50 kilobytes to 100 kilobytes, consider splitting it up. That will allow you to take advantage, once again, of that parallelization. And avoid large inline scripts. Now this might be one of those things that isn't entirely intuitive. When you have large inline scripts in your page, that makes it really, really hard for JavaScript engines to apply optimizations like this script streaming, because we can't just easily hand that work off. We have to actually keep parsing it in the same page and on the main thread. So those are a few things that you can do. I was saying earlier that in the past I've spent a lot of time talking about the cost of parsing and compiling code. Now, V8 over the last year or two has been focused on trying to optimize parsing as much as possible. And here's a latest round of updates from what we've been doing. So in the time that it took Chrome 61 to parse just Facebook's JavaScript, Chrome 75, so Chrome Canary, can now parse both Facebook's JavaScript and 6 times Twitter's JavaScript. There's a huge improvement there in terms of our ability to parse code. So parse and compile is less of a cost than we used to think it was. We can actually now do quite a lot of it without blocking the main thread, but depending on the patterns that people use, this can change. If you want to visualize this, it looks a little bit like this. So this is Chrome 48 on one side of the screen loading up Shakira's page on Facebook, and that's Chrome 75. So one of those loaded up in 3 seconds and the other loaded up in 11. This is just one example of where, JavaScript performance is kind of a partnership where, on the browser side, we're going to do as much as we can to load your code efficiently. But if you can do things like just break up your work a little bit more, that really helps us quite a lot. Another thing I wanted to talk about is sort of the post-initial load experience, so repeat visits. And that's where code caching comes in. So V8 and other browsers have got this concept of a code cache. And the idea is that if there are scripts, if there are experiences where your users are coming back to them pretty frequently, so imagine someone coming back to your site, 3 or 4 times within 72 hours, we can actually take that as a signal that that's an experience they're going to benefit from, us loading a little bit more efficiently and storing a little bit more bytecode around. So what we do is, if you do hit an experience 3 times within 72 hours, we'll store metadata about those scripts and we'll store the bytecode representation. And we can actually skip a lot of the cost of parsing and compiling code and go straight over to execution time. What this means is a 20 to 40% improvement in overall parse and compile during page load. You might be asking, great, this is a browser optimization. I don't care. What do I have to do to take advantage of this to the max? So one thing that you can do is just be careful with what you're putting into your JavaScript bundles. If you're including vendor code, so vendor code being your libraries, your React, your Vue, your Angular, if you're including those in your main bundles and you're regularly invalidating your JavaScript bundles, that's going to defeat optimizations like this. This is one of those reasons why it's good to break up any code that's not going to be frequently changing into a separate vendor bundle and keeping your application logic, your state management, all of those things in one bundle or separate bundles, and keeping your vendor bundles in another place. So to recap so far, download times are pretty critical for low-end networks. Try to ship less code, minify that code, take advantage of modern compression schemes like gzip, like Brotli, to try limiting how much you're sending over the wire. JavaScript execution time is pretty critical for phones with slow CPUs. So on the server, in the past when we've been more focused on server-side rendering, you tend to get what you pay for in many ways. You can easily see what the CPU cost, the disk cost, the network cost is going to be. And as we build sites that are more heavily based on client-side script, we sometimes pay for those experiences in ways that are not always very transparent and easy to tell. So keep an eye on your JavaScript execution. Keep an eye on what you're sending down to your users. Now, I mentioned earlier that I spend a lot of time talking to developers about JavaScript. I also spend a lot of time taking a look at JavaScript bundles and questioning what's in them and why. So one thing that you can do to kind of work around JavaScript bloat is code splitting. Now there are many different approaches you can take to this problem. You can split by page, you can split by route, you can split by component if you want to go really, really granularly. You can split your large bundles into very coarse, very fine bundles that, again, can take advantage of that parallelization. And if folks are less experienced with what code splitting means in practice, here's a very quick example. So here we have a stock market application where if you go and you click on any of those entries, it'll open up this larger chart component. But that chart component is not critical for the initial load. That could be loaded on demand. And so in this React app, we can move away from statically importing in that component. This is just a static import. We're starting off with a single large bundle where all of our code for this experience exists in one single main.js file. It's about 125 kilobytes in this case. And by taking advantage of some of those newer capabilities that have come to React, such as React.lazy and suspense for code splitting, which you pair with Webpack, we can actually split these bundles up to improve our initial load performance and to improve our time to interactive. So if we break this work up, we can end up with a 36 kilobyte main script size, which is relatively small. And then when the user actually starts tapping on those individual items to display that chart, we can load that code on demand. So that 89 kilobyte chunk can be loaded on demand. You can do all sorts of interesting, fun, and funky things here. You could be prefetching those bundles ahead of time or using a service worker to cache them ahead of time. But this is the general idea, just breaking up that work. Now, code splitting can be done in many, many weird and wonderful ways. I've seen people try things like lazy loading on visibility. So you use intersection observer, and as you scroll through the experience, as components come into view, you then decide to load any of the critical path code that's necessary to boot them up. Earlier, I mentioned that the rehydration can be a problem. And so it's been really exciting to see that many different framework communities have been talking about progressive rehydration lately. So here is an example that we have where we're server-side rendering an application with a very, very thin amount of script necessary to attach the event handlers to these buttons. And when you tap on any of the buttons, that's the point when we're actually hydrating the experience, hydrating the components, we're fetching any of the dependencies that are necessary for the experience. And with this approach, your individual pieces of your server-side application end up booted up over time instead of that current approach of initializing your entire application at one time. So you're hydrating on interaction instead. So I'm excited about this. The Angular team are doing lots of interesting work in this place. React are currently exploring what progressive rehydration might mean upstream in core. I've recently also been really excited to see that the Vue community are also playing around with some of these ideas. So there's a really great article. If you're a Vue developer, there's a really great article you can check out that talks about how you can hydrate on interaction with components or how you can hydrate on visibility of components. And just looking at the Lighthouse stats here, we can see that opting for these approaches can have a meaningful impact on time to interactive and on things like estimated input latency. Code splitting is a real optimization used by real sites. So over the last couple of years, we've seen quite a lot of sites adopt it. Both Twitter and Tinder were able to improve their TTIs by almost 50% by adopting code splitting. Twitter's in a really interesting place. They now have 40 or 50 on-demand chunks that are loaded as you kind of navigate through the experience. So you're not paying that upfront cost of all of the script at one time. Now, if you're not really sure where to start with code splitting or what in your experience you might want to break up, the DEVTOOLS have got a code coverage feature that you can use. And the idea here is basically that you load up your site, you start interacting with it, and we'll continue showing you exactly how much code was hit, like what code paths were hit, what code paths were not. And you can then dive into the sources panel and you can see, okay, well, maybe these modules are not really as necessary. Maybe these components can be lazy loaded at some future point in time. Continuing with the theme of JavaScript bundles being quite large, I find myself in this position quite a lot of just questioning what is in those bundles people are sending down. Luckily, there's some really good tooling available for folks to check out. Something that I use on a daily basis is Webpack Bundle Analyzer. It's phenomenal tooling. It gives you a really nice visualization of everything that's in your dependency tree. You can also use Source Map Explorer, which is a similar tool. But the basic idea is we often end up npm installing things into our experiences without fully understanding the cost of those things. I sometimes say that NPM is kind of like, the Tinder of node modules. You don't really know what you're going to get. So it's very important to understand the cost of each thing that we're going to install. And there's some good tooling to take a look at it. Some very quick tips. Be careful when you're using things like Moment.js. In some of my apps, I've found that by dropping Moment.js in place of alternatives like DateFNS or Luxon, I've been able to shave 50% off of my bundles. So check out sort of some of the alternatives to Moment. I think this was mentioned yesterday, but just be careful with including full-fat Lodash. You often don't need all of it. You can probably just include the exact methods that you need. And there are some good Webpack plugins that can actually help you kind of strip away parts of Lodash that you don't need to use. So take a look at that as well. At Google, we have this kind of system that we use called conformance, which enables us when we're building out applications to kind of flag and say, well, here are some best practices that maybe you should be following. Here are some things that maybe you shouldn't be doing. And one of the things that falls into kind of an interesting place there is this notion of maybe disallowing large imports into our projects. So something you may or may not be familiar with is that ESLint actually has this really, really powerful rule called no restricted imports. And what it allows you to do as a team is say, if there are any packages that I'm going to import into my page, maybe as a team we want to say, no, you can't import them. You have to use these lighter alternatives. And what this will do is it can either error or warn when anyone on your team is trying to introduce a large dependency into the project. I found this really interesting. It's very flexible, allows you to add in sort of your own custom rules. So this next one might be contentious or it might not be. I personally don't feel like static web pages need 300 kilobytes of JavaScript to be good. I see a lot of experiences today where we could just be shipping down something lean, but instead we're opting for convenience. What's convenient to us in many cases. And it's been very interesting to see kind of other large sites understand that this is a problem, and there are thankfully some interesting solutions to it. So about a year ago, Netflix did a bunch of analysis on their non-member landing pages, so the overall sign-up flow for signing up for Netflix. And what they discovered was that although they're using React on the server side, they were paying quite a lot of a cost on it for some of these entry pages to the experience. And so what they did was that they removed React and other libraries from their client-side script bundles. They replaced it with vanilla JavaScript. And they prefetched React for pages further down the funnel. So any of those more complex pages on Netflix.com, the video players, et cetera, that you're seeing, those are things that they're prefetching. So you can still get the benefit of using React without necessarily using it on every single page, for example. Very recently, a retailer in Indonesia called Tokopedia saw Netflix's case study and they decided to borrow a leaf from their book and do something very similar. So they rewrote their landing pages, moving away from React, porting them over to Svelte. And what they discovered was that between that change and other changes, they were actually able to reduce their JavaScript bundle sizes from 320 kilobytes down to 37 kilobytes for those pages. A massive improvement. Now they're still prefetching React for the more complex things further down their funnel, their funnel. And the idea here is just to try finding balance between developer convenience and user experience. One final thought I've got is that I think that, and this kind of came up a little bit yesterday, but we need to make performance more of the conversation at our organizations. Very often the engineering teams that I speak to end up being the only ones that own performance, or maybe you're the only performance engineer at your team and you're constantly fighting back against bloat. And so, if you're that person, you've probably experienced this, this problem of fixing a site and then a teammate coming over and just blasting all of your work away. Like, I just fixed it. Why did you ruin it? And so I think that we need to get to a place where hopefully between organizational buy-in to performance, quantifying why performance is important, quantifying why individual features and PRs are important, we can start to evolve some of these conversations. I talk a lot about performance budgets, and I think that they're really important. I see a lot of the sites that I talk to ending up regressing after a big amount of performance work. And budgets are great because they help you hold the line. They're kind of this agreed set of targets that you and your team can strive for. And you can set budgets for all sorts of things. You can set budgets based on timing metrics like time to interactive or FCP. You can set them for quantity, so JavaScript bundle sizes. You can set them for rules like Lighthouse scores. And the overall idea is, maybe providing more insight for all of your team members into the cost of their work is going to help. So I see a lot of people trying to integrate these concepts into their CI, trying to get dashboards and reports put together with things like speed curve or caliber so that they can share performance insights and where you're falling off the path with other stakeholders. Still a lot of interesting work for us to do evolving these conversations. So I hope that some of this was useful. I'd like us to try to stop taking things like fast networks, fast CPUs, and high amounts of RAM for granted. This is a problem we still run into at Google. Like I'll have people on my team who are mostly testing things on an iPhone or a Pixel 3, but not devices that are representative of what like the average person is trying out there. So let's see if we can try to test more on real phones, test more on real networks. I know Pat Meaden's in the audience, so web page test is really, really great for just validating what your experience is going to look like on real world devices with a network that's a little bit closer to real world as well. And one of the reasons this is important is, again, those devices have such variance. They can have differences in CPU, GPU, L1, L2 cache, and you want to just make sure that the things that you're building are going to look really, really good for the end user at the end of the day. So improving performance is a journey where lots of small changes can sometimes end up leading to pretty big gains. So I hope that you take something from this talk and can apply it to your real-world sites. I also hope that, at least with some of the more engine-specific stuff, that it wasn't too over folks' heads. And it's also perfectly okay if it was. I don't expect people to go and start trimming down 90% off the size of their JavaScript bundles today. It's kind of like, the experience you have when someone asks you to go and draw something like a baby. Step 1 might be drawing the outline of the baby. Step 2 is definitely not this. In almost all of my projects, my step 2 has looked a lot more like this, where I'm just iteratively trying to strip back some of my dependencies and make a few small wins that lead up to big gains. So I hope this was useful. When in doubt, measure, optimize, and monitor. Hope this was useful. Thank you.